Here is another example. And in this example, we will have 3 by 3 matrix. And the reason why we have 3 by 3 matrix is because we have 1, 2, and 3. Okay, so change this equation into a 3 by 3 matrix. So a 3 by 3 matrix is this: 1, 1, 2, 1, 3, 1, 2, 2, 2, 2, 3, 1, 3, 2, 3, 3, 3. Okay, so all we have to do is just fill in the correct spot. Okay, so 1 is right here, so we put 9. Where did the 9 come from? That is the coefficient for that spot. Next, 2 is right here. This is 2, so we put 7. Next, this is 3, so 3 is right here, so we put 11. Okay, next, if you notice, we have 1, 2 here and also 1, 2 here. Since there are 2 spots, we will divide by 2. So divide by 2, so -8 divided by 2 gives me -4 here and -4 here. That's what I have. Okay, next, 1, 3. So 1, 3 is in this spot and in this spot. So 1, 2. And there are 2 places, so 8 divided by 2 gives me 4 and 4 here. We do not have anything for 2, 3 and 2, 3 here, so we'll just put 0, 0. All right, so one more time, know how to change this equation into the matrix form. This is the first spot, this is the second spot, this is the third spot, just the diagonal only. 1, 2, there's 1 here, there's also another 1 right here, so divide by 2. So -8 divided by 2 gives me -4 and -4. 1, 3, here is 1, 3. I have another 1, 3 here, so there are 2 places. So 8 divided by 2 gives me 4 and 4. There is no 2, 3, and there is no 2, 3 here, so we put 0, 0. Okay, so again, make sure you know how to change this equation into this matrix. Okay, next, and if you look carefully, I didn't write it out, but if you transpose this, it will come back to the same. So A and AT are symmetric. So column, row, okay, column to row, column to row, column to row. It is the same thing. So A and AT are exactly the same. They're symmetric. Okay. Next, again, there's going to be a lot of step that I am skipping. So we need to find the determinant of A using lambda. Okay. So this is what I have here. Using cofactor, multiply all this out, combine like terms and whatever that you need to do, and factor them out using synthetic divisions and so on, and it will come out to be the eigenvalue of 3, 9, and 15. So when you do the determinant of this using cofactor, multiply all this out, you will get that polynomial of lambda cube and all the way down using synthetic divisions so that I can find the factors, and it came out to be 3, 9, and 15. Again, a lot of steps are skipped. I hope you remember how to get them, know how to do them so that I can get the eigenvalue 3, 9, and 15. Next, again, a lot of steps are being skipped. So eigenvalue 3 will give me regular eigenvector. Regular eigenvector will become the normalized. Okay, eigenvalue, regular eigenvector. Change this regular eigenvector into the normalized. Same thing with the last one. 15 becomes this eigenvector, regular. Now change this regular eigenvector to become the normalized. Okay, so all three of these vector is considered normalized eigenvector. It came from the regular eigenvector. Regular eigenvector came from the eigenvalue. Eigenvalue came from finding the determinant. Okay, and then after that, write the normalized eigenvector into this form. This right here is our diagonalized vector matrix, diagonalized eigenvalue matrix. Okay, so this matrix right here only contain the eigenvalue. Okay, and our job is to write this matrix into Y form. As you can see, one spot, 3, second spot, 9, third spot, 15. And there's nothing here, so we don't need them. Okay, so that's our objective, is get the diagonalized matrix with the eigenvalue and just write it as 3y1, 2 plus 9y2, 2 plus 15y3, 2. So first spot, second spot, third spot on the diagonal matrix that contain the eigenvalue. Okay. So again, be very careful. Know how to write this equation in matrix form. After that, find the determinant so I can get the eigenvalue. Use the eigenvalue to get the regular eigenvector. Turn the regular eigenvector into normalized eigenvector. Our objective is to get the diagonalized matrix, diagonal matrix with the eigenvalue, turn it into Y form. Okay.